Welcome back everyone. So today I have picked up another interesting problem from electrostatics, although I believe it's majorly a mechanics problem because very little concepts of electrostatics are involved and mainly it tests your mechanics understanding. Okay, so I'm reading out the problem once. A particle A of mass m and charge minus q is at rest at a distance r from a fixed body B of charge plus q. At t equals to 0, A is given an impulse of mv perpendicular to the line joining their centers. Ignore any form of gravitational interaction between the particles. Choose the incorrect statements. And k is given, as we all know, 1 by 4 pi upon epsilon naught, the electrostatic constant. And we're given four options. First two options are related to the time taken to reach to the initial position if the trajectory is closed, right? Otherwise it will never return. It can be a possibility that the particle will not return to the initial point. We'll figure that out in the problem, in the solution, right? And option C or D are related to the ratio of initial kinetic energy and initial potential energy. By observing the ratio value, we can conclude the nature of trajectory, right? So these two options are about that. So I think a few concepts beyond JEE syllabus is required to solve this kind of problems, and it's very much helpful for Olympiads. But if JEE asks, there is a rare possibility because it's JEE Advanced plus level, I would say. They will ask in the comprehension section where they will give you the polar form of a conic section and all the necessary informations that are not being taught in JEE syllabus, but you will require in this solution, right? So I have written the equation of conic polar form that r equals to ed upon 1 plus e cos theta, where r is the distance of any general point of that conic from its focus, and d is the distance of focus from directrix, and e is, as you know, that eccentricity, right? And theta is the angle subtended by that radius vector. Okay, so just rearranging the terms, we'll get this, that cos theta equals to d by r minus 1 upon e. And now we'll differentiate this this equation, both sides, with respect to time, because later on we will require the dr dt value. So differentiating just using the chain rule, I'm not explaining a differentiation, I guess it's not required as well. So dr by dt will get ed upon 1 plus e cos theta square into e sin theta, and d theta dt term will be there as we differentiating with respect to time. And using that original equation, that r square I'm writing here inside, r square equals to e square d square upon 1 plus e cos theta square. So we can substitute using this one. Here you can simplify the dr dt value a bit and we will get to this one. The dr dt equals to r square by d into sin theta d theta dt. Right, I'm keeping it here, but we'll require this value later. I'll come back to this. So now I'm writing E. E is energy, total energy. Total energy of that moving particle. Moving particle is A, I guess, right? Yes, and B is the fixed one. So we'll have the electrostatic potential energy, that is minus of K capital Q small q upon R, where R is the distance between those particles, and this part is the kinetic energy, but I have written like this because you will have two components of velocity, right? One is tangential and another is radial. So radial one will be dr dt. These two are perpendicular to each other, right? And r d theta dt, or we frequently write that r omega is equals to v, right? That v tangential equals to r omega, and omega is the angular velocity. So I have written that only, that r d theta dt square. So this is basically vt, if I write like this, tangential velocity, and this one is radial component vr square. So net velocity v net square will be vr square upon vt square. This one only I have written here, maybe looking like a bit complicated, but that's a simple one. So now I'm proceeding. Next step, I'm keeping this term as same, and now write L. L is the angular momentum. of the particle with respect of A with respect to the point B, I mean the fixed point. So I can write it as m v r. We write that L equals to m v r very often, that v is tangential. Maybe we are supposed to determine the angular momentum from this point, and this distance is r, and this perpendicular velocity is v, and the particle's mass is m. We write L as mvr about this point. So this one only I have written that m r and r d theta dt is a tangential component, because radial component of velocity will not contribute to the angular momentum, as you know. So I'm rubbing a few things just to make the solution a bit clear. So yeah, that's all. And here I've simplified, right? That first term, if you multiply with this one, it will be half m r d theta dt square. So using this one, I can write that term as L square upon 2 mr square. I'm not explaining the calculations. I've written the solution already just because of minimizing the time, because it's a bit too lengthy calculation. Olympiad type problems usually have this kind of calculations. So, and when you multiply half m with the second term, half m dr dt square, this is the half m, and that's why I've differentiated the r term just to get the value of dr dt. And you will get dr dt in terms of d theta dt square and sine square theta and all this. So if you have d theta dt square, you can relate that with this equation, L equal to m r d theta dt into r. And you will get also one sine square theta term, that sine square this one actually sine square theta, this is actually sine square theta term, and I have written this as 1 minus cos square theta terms, and here is the cos theta. I have already find out. That was the purpose. So you just once go through this calculation. I think you can understand this by your own. I'm not spending much time on the calculation part, and just simplifying the terms, will get something like this: minus kq upon r plus L square by 2md square whole multiplied by 1 minus 1 upon e square plus L square upon mred. Okay, so now I have clubbed the 1 by r terms one together, and next L square upon 2md square multiplied by 1 minus 1 by e square. Okay, so this one is a constant term, as angular momentum is always conserved because the particle is moving at a central force. I mean, the force vector is always passing through the focus point through which A is revolving around, right, and B is fixed at that point only. So this one is a fixed part, I mean the constant part, and but this one is variable because r term is involved, and radius value, I mean the distance from the fixed point, will change by the moving particle. But as energy is conserved, so you can state that E should be independent of R, because if it is dependent on R, we will get different energy values at different positions, but energy conservation principle should not be violated. So we can conclude that this term will sum up to 0, that L square minus med minus k capital Q small q. From there I have got this result, that L square equals to this. Also L equals to m v naught r naught. V naught and r naught are the initial speed and distance of A from the fixed body, that is basically B. Okay, because from fixed point we have perpendicularly given the impulse. Let's say this one is the m, this is A, and this is B. This one is having velocity v naught and this distance is r naught. So L must be m v naught r naught. Okay, so yeah, the purpose of assuming v naught and r naught is just to relate with that initial energy values ratios, right? We had two options regarding that initial kinetic energy and potential energy values. So this one is the energy term I have already got, and I'm equating this with the initial total energy. Initial total energy was half m v naught square minus kq capital Q small q upon r naught. Initially the velocity was tangential only, there is no radial velocity, so v naught is the net velocity only. From there, if you again do the calculations, you'll get something like this. So I think these steps are self-explanatory, but yeah, this one is a catch. Not catch, I would say, but rather substitution, because D we have assumed, right? D was not given, or rather we are not even interested in finding out the energies in terms of D. We want to get the term R naught so that you can relate the initial energies. So I've written D as R naught upon R naught by E, because if you put theta equals to 0 degree, the initial condition, you will get R, that is basically R naught at theta. Putting theta equal to 0, I'm putting theta equal to 0 in this polar form. Putting this, we will get Ed upon 1 plus E, right? Ed upon 1 plus E. So R naught upon E will be D plus 1 upon E. Now you add these two terms, R naught plus R naught by E, you will get this as D. So that's the simple substitution I have done here. And again, rest you can understand by yourself, and got to this result, that 1 plus E upon 2 is equals to half mv naught square upon k q upon R naught. This is the initial kinetic energy. This one is initial kinetic energy, and this one is initial potential energy. Okay. So for now I am checking the options that was related to the trajectory and initial energy values. For hyperbolic trajectory, eccentricity should be greater than 1. So 1 plus E should be greater than 2, or rather I can say 1 plus E upon 2 should be greater than 1. All are same. So from there I got this result, that kinetic energy should be greater than potential energy at initial condition. For parabolic trajectory, eccentricity 1, so energy ratio value will be 1. So let me mark first this correct options amongst here. Sorry, we are supposed to find incorrect. The ratio of initial kinetic energy of magnitude of potential is more than half. Its trajectory is hyperbola. So what we got for a hyperbola? Let me check once, I forgot. For hyperbola, kinetic energy is greater than potential energy, right? And here it is asking the ratio of initial kinetic energy to magnitude is more than half. Yeah, it's true. Kinetic energy was, the ratio was greater than 1, so it should be also greater than half. If the ratio of initial kinetic is 1, the trajectory is a parabola. But wait, one thing. No, I don't think C is correct one. D is absolutely correct, but if it is greater than half, it is not necessarily that its trajectory will be hyperbola, right? So you should read the statement quite carefully. If it was the vice versa, the trajectory is hyperbola, then the ratio you can conclude that it will be greater than half. But if the ratio is greater than half, it may or may not be hyperbola, because greater than half does not ensure that ratio will be greater than 1 as well. So C is one of our answer, and now we are left with two options, A and B. So as you can clearly understand, for hyperbola and parabola, the particle will never come back to its original position. So for A and B options, the trajectory must be ellipse, because ellipse is a closed trajectory. In that case, we will have the particle to be back in the same position from where it started. So as you know, area of ellipse is pi AB. I have not defined the AB. By convention, I have written that A and B as semi major axis and semi minor axis respectively. So here I have shown the calculation that R naught, the initial separation, was A into 1 minus E, and as you know that A into 1 minus E, it was the perigee, right? Because perigee is closest to focus than apogee. Apogee was the away point. So yeah, R naught was A into 1 minus E, and E square is 1 minus B square upon A square by convention. From there you can relate this B as in terms of A and E, and then you can also put the A value in terms of R naught and get this B value. So this one is the B value, and this one is the value of E. I have written all the stuffs in terms of R naught and E only. Now I am supposed to substitute E also. So from 4, let me show the equation. This one, the fourth equation, we'll get 1 plus E equals to this. So 1 minus E will be this. So 1 plus e and 1 minus e values are also put in this equation, and you just proceed with the calculation. I'm not spending much time here. You will get this result. So this one is the area of the ellipse. And as you know, in Kepler's law, that areal velocity is a constant term in gravitational or whatever be the field. When the particle is moving in an elliptical path, Kepler's law are valid, and you can use this. So areal velocity, this is the areal velocity, I mean the amount of area covered in unit time, or DADT in differential form. So as this is constant, you can simply write the areal velocity into total time to be back at the same point from where it started. This product will give the area of the ellipse. So I'm just equating these two terms, and from here I'll get t as this. So yeah, let me mark the correct option. Oh, sorry, again I forgot, we are supposed to find the incorrect one, right? This one is correct option, this one is incorrect. So A and C should be our answer for this question. So yeah, it's a bit calculative question, and some concepts are also beyond JEE syllabus, but very much helpful for Olympiad aspirants. And as I said, JEE can ask this kind of questions also in comprehension section, where they put an overview of that out of syllabus topic and then ask some questions based on that concept. So you can practice this kind of questions. These are very good practice for JEE Advanced as well, besides Olympiad, because it will give you an edge over the other students. So that's all for today, and stay tuned, I'll bring some more interesting problems.